Hello, thank you for your interest in this online seminar about the quantum machine learning. In this week, we are going to learn the Barren-Plateau issue in the quantum machine learning. In this presentation, I will give a brief presentation on the paper Barren plateaus in quantum neural network training landscapes. And first, we want to answer a question: what is variational quantum circuits? Variational quantum circuit, which is short for VQC, is also known as the parameterized quantum circuit. It aims to optimize the parameters theta by numerical approaches, such as gradient descent, to minimize the cost function. So before we move to the next step, first we want to introduce some notations. Direct symbols. And here, direct symbols are used to describe the quantum states. For example, here, this we call this a brag. Brag is a row vector, and cat is a column vector. And here we shows two examples as to illustrate what is the bread and the cat. For example, the bread is a row vector. Here, 0 means that in the 0 position, the value is equal to 1. And similarly, for the cat, 1 means that in the position 1, is value equal to 1. Oh, by the way, here you show this is the dot T denotes as the transpose. We use the transpose on the row vector to represent the column vector. And this symbol pronounced dagger. Dagger denotes a conjugate transpose operator, also known as the Hermitian conjugates. And here, besides we denote the transpose, we also denote the star symbol as the complex conjugates. And cost function. Common cost function, E theta, is the expectation value over some Hermitian operator H. This H means the H matrix. So here we use this formula to denote expectation. Also, this formula is used in the paper. And here we assume that the initial state of the VQC is this, and the end state is this. And Barren-Plateau issues. So here is this paper, how it describes the Barren-Plateau issues. And if VQC satisfies some conditions, in this presentation, we will simplify that. So we just skip some details. If you're interested, you can go through the paper to see what condition will cause the Barren-Plateau issues. And in the paper, it mentioned that if the VQC satisfies some conditions, when we train the VQC, then the mean value of the derivative with regard to the theta k is equal to 0. Also, the variance will decrease exponentially as the number of qubits increases. And in other words, if we have the Barren-Plateau issues, it means that all the gradient-based method will fail as the gradient is very close to 0. So we may want to ask some questions. First, what condition may cause the Barren-Plateau issues, and how to avoid these issues? So we directly go to the conclusion. And for the first question, what condition may cause the Barren-Plateau issues? According to the paper, it says that as the number of qubits increases, and when this number of qubits is very large, and it may cause the Barren-Plateau issues. Another one is the VQC is random enough. This is another reason that may trigger these issues. So in the paper, it shows some experimental results to support these claims. For example, we can see in the figure 3, it shows the exponential decay of the variance. The y-axis is the variance, and for the x-axis, it shows the number of qubits. And we can see the slope of this fit line is the indicative of the rate of exponential decay as determined by the operator. On the right-hand side, in figure 4, it shows that some relationship between the variance and the number of layers. And the y-axis still the same. It shows the variance. And for the x-axis, it shows the number of layers from 0 to 500 approximately. And for this line, for each bit, the different lines corresponding to all even number of qubits between 2 and 24, which means there's 2 qubits, this 4 qubit, and so on. So in these figures, we can tell that the convergence of the second moment as a function of the number of layers to a fixed value determined by the number of qubits. So through these two experimental results, we can say that as the number of layer increases, and we can say the variance will decrease to the number very close to 0. So another conclusion we may want to know is how to avoid these issues. According to the paper, is that the first potential solution is that we want to control the number of qubits, which means that the number of qubits cannot be too large. And it makes sense. And usually the number of qubits could be set under 10 so far. That would be good for the simulation. And another potential solution is that we may want to constrain the distribution of VQC. For example, we give a prior distribution on the VQC. Or for some current recent research, and some researcher, they give some specific initialization, let's say some beta distribution or Gaussian distribution, so to make the VQC less randoms. These two potential solutions may help at this point. So this also gives us some new ideas, or some new direction how to solve the Barren plateau issues. Thank you for listening. Any questions?